Alright, so once again, my name is Jenny Lay. I've been working with Carrie Moran in Professor Kimberly Turner's lab this summer with the Department of Mechanical Engineering in microcantilevers as mass sensors. So let me tell you about what microcantilevers can do. So some of their applications include airport security, military use, as well as use for food and drink. So in the military, you can use microcantilevers in order to in airport security, you can use microcantilevers in order to detect different explosives, bombs, harmful weapons, etc. So security personnel will know that there's a threat to the building. Military use include using microcantilevers in order to determine if an area or an environment is safe from harmful chemicals or substances, etc. They can also be used to find contamination in food and drink. So what is a cantilever? A cantilever is an object that's fixed at one end and free to oscillate at the other end given a force. These cantilevers, an everyday example of a microcantilever would be like a diving board, except it's big. And these cantilevers, they oscillate at their natural frequency, which depends on both the length of the cantilever as well as the mass of the cantilever. For my project specifically, I'll be focusing on the mass of the cantilever. So the length of the cantilever will stay constant throughout the entire project. So I said that I'm going to be working with microcantilevers. However, I will be testing at the macro scale. So micro is on the scale of the diameter of a human hair, which is about 70 to 100 microns across. And they're obviously very small, so it's much easier to test at the macro scale. So the methods and techniques that I test at the macro scale can be used and applied at the micro scale. So with some initial experimentation, we discovered that, or proved that as mass is added to the cantilever, the frequency at which it oscillates decreases. So this can be used as mass detection. When you notice a change in frequency, you know that there's a change in mass of the cantilever. If you notice the previous slide, these peaks are pretty obvious, right? They're peaks. But not all the data that we collect look like this. Sometimes they look like this, more of a bump in the road kind of thing. And when you look at the graph on the left, there's two sets of data, except because of the bump in the road kind of peak, you can't see the difference in frequency as well as you can if you had two obvious peaks. And so this is the reason why we need amplification techniques. We need to amplify our results. So if you look at the graph on the right, the blue represents kind of that bump in the road, and the black represents the results after they've been amplified. So there's an obvious difference. So this is our lab setup. We start with a computer. We send a MATLAB code to the function generator. The function generator controls the shaker and tells it, this is the frequency you start at, this is the frequency you end at, and this is the amount of time you get to do it. And so the shaker shakes and excites the cantilever. The cantilever has an accelerometer located at the very end. And as the cantilever oscillates, the accelerometer can track the motion of the cantilever and send this information to the spectrum analyzer. The spectrum analyzer can then display our data in like the graphs that we got. So I mentioned our amplification techniques. The first one that we tested out was parametric amplification. So this is somewhat similar to someone on the swings. So when you're on the swings, you pump your legs back and forth in order to increase your amplitude of motion. So that's kind of what we do for parametric amplification. We want to increase the amplitude of motion. So what we do is we change a parameter as a function of time. So every trial that we run, we change that value for the parameter. And the term that involves this parameter is multiplied by the displacement of our curve, which then gives us the effective stiffness of the cantilever. So as I change the parameter, I also change the stiffness of the cantilever, which ends up changing the amplitude of the curve. So these are results for parametric amplification. If you notice that as those peak higher and higher, we're decreasing the stiffness of the cantilever. So the light blue represents the original frequency sweep without any amplification. And the black represents the highest peak we could find with amplification. And with this method, we saw a 40% gain in the amplitude. Our other amplification technique is Q control. So we start off with a cantilever, and it sends out a response signal. And it may look something similar to the graph right here. And once we have that signal, it's sent through a filter. And this image isn't quite the same scale as the graphs. However, it illustrates the purpose of the filter. So the frequencies that start here and it goes to here, those are the frequencies we want to keep. So that data that's between those frequencies stay, but all the other frequencies outside of that range is eliminated. So we isolate just the natural frequency of the cantilever. So after it goes through the filter, the graph looks like this. So you notice all this like noise right here is just taken out, and you only leave the peak. So once that is done, you amplify your results, and then you phase shift. So your input, your output curves could look something like this. They won't like line up on top of each other. And so you want to correct for that, so you have to phase shift it. But once that is done, you use the frequency which you found for this natural frequency, and you input it back into the cantilever, and you use that to actuate it. And so this cycle is repeated over and over, and we did it for 10 times. So these are our results for Q control. Normally for Q control, you don't actually use a frequency sweep, but it's plotted on this graph just so you can compare the two. So the blue is the frequency sweep for the cantilever, and the red shows the results from Q control. The method is called self-excitation. And so here we saw 115% gain. And the winner is Q control. So these two graphs are plotted on the same scale, and you notice that the light blue for parametric amplification and the dark blue for Q control are at the same height, they're at the same amplitude. But for parametric, it only goes up to where the black is, and this one goes obviously higher. So in that sense, Q control is the obvious winner. Another thing is, if you notice on parametric amplification, when it starts going up to the peak, it's kind of rounded in, whereas Q control is much steeper. And so that means there's a lower signal to noise ratio for parametric amplification. So in that sense, Q control is also the better choice. Another thing is, when running parametric amplification, I had to run 4 extra trials here in order to get my results. And each of these trials, depending on how complicated the code is, could range from about half an hour to sometimes over an hour to get your results. Whereas for Q control, I only had to run it once, and that took about 10 minutes or so. So time-wise, Q control is also the winner. So overall, Q control is just better. So for future work, you would use Q control to amplify all the results you get from your testing, and then in the long term, future goal is to use these microcantilevers in everyday life. And special thank you to Carrie, most awesome mentor ever, and Professor Turner, most awesome advisor ever, and as well as EUREKA and Matt for their input on my presentation, as well as the program. Any questions? Yes?